Yeah, hello. I will start with this video, and it's about the module 4. My name is Albert Claudia. Yes, the word now I'm going to talk about handwriting recognition, and the issue is very simple. This is about the handwriting digits and how we can classify these digits. And to do it, so I have, of course, to have access to the database. Like in this case, it will be the Modified National Institute of Standards and Technology, means, who have collected, has a database, yes, of handwriting digits. So we can imagine that each digit, okay, it's like an image, and it has, of course, a format. And the format is in this case 28 times longer 28 pixels. That's the solution though. And this which means that we have 785 or 85 features or pixels, and it is the number of the columns. If we can think that we have about the database has 70,000 image, and where each image has uh, 785 columns, 785 columns. And this is the input. This will be the input for our database for this. And now I have to implement to solve these problems, and I used the language R, and there is a package MXNet-R, which is one of the most popular, yes, for deep learning. And the procedure will follow is that first we have to load, of course, the training data set, and then I will separate the data sets, so it will be 80% for training and 20% for testing them. After that, so it's only to train the model, and then so to use the model to predict and see the result of this. So, well, as an architecture, I will choose. There is this one, and as you can see, I use two convolution layers here. This is the first, this is the one, and this is the corresponding pooling here, two pooling layers also now. And finally we will have a fully connected layer, which consists of hidden layers, two hidden layers, and finally the software. The output will be the softmax matrix. Now if we'll talking about more about the details about this architecture, and we have here the hyperparameters now. For convolution layer 1, it's of course that we have first of all the input is this 20 28 and 28 pixels. It's totally it will be 784 inputs now. And the first convolution layer, in this case, it's about 20 filters, and the size will be 5, and then pulling max the size which the size is 2 over 2. And we are going to use an activation function, nonlinear ReLU, and try to put in 0. For the convolution layer 2, it's the filters, the number of filters is 50, and the size is the same of the first layer, phi gamma phi, and this the pooling, and we have also, of course, it's a pooling layer max and activation tray. And finally, it's that's the um, fully connected layers, which consist of two hidden layers, one and two. And in this case, we have 100, 500 units neurons, and in this case, 10 units. And we just use use our code as I said before. In this case, for the two convolutions layers. And the reason here is now, of course, to extract a rich representation of the input if the input matches. Yeah, we use, of course, this. So we can look here. This is the for code for the first apply, and the first of all, we have this the full convolution layer. In this case, we have we use 50. The number of filters is 20, and the size of the kernel or filters 5. And this activation function is ReLU, ReLU type, and finally we have a pool layer also here, and the size of this is number 2. And the same for the convolution layer 2. Now the difference that in this case we have here 50 filters, and here the same, and the size is right. So next we'll call also this for the code for the fully connected layer. This is for the first hidden layer. So there it's 500 units, and they have also a ReLU activation function. And the second hidden layer, in this case 50 layers. And finally we have the output result. It's the matrix will just show the result. Means that you can write in percent how many they like. So after we have trained the model, we have to predict also. When we have training the model, and we'll test in the model, so we can run this model as